So once again, let me briefly remind you what we did up to now. So we want to enumerate maps. In order to do that, we want to compute weighted sum over a set of maps. And we did build some generating series for these numbers, for these weighted sums. And what we found out first is that we can associate to this problem an algebraic curve, a Riemann surface, which is obtained just by looking at the generating series of genus 0 maps with one boundary. Now, what we did prove is that even though this generating series is a priori as a function of x, just an asymptotic expansion around x goes to infinity, we can promote it to a well-defined monovalued rational function on this surface sigma. So rational function on a parameter, which is a coordinate on this curve sigma. And even more, we could show as well that W02 could be promoted to such symmetric function, which is monovalued when you define it on the same Riemann surface here. Since what we want to compute are these numbers, which are obtained just by computing residue, what makes sense is not to consider functions, but consider a differential, which you can integrate. And so we define some omega GNs, which are just obtained by multiplying these WGNs by a product of the x's. Using a generalization of Tutte's equation and writing it in terms of this generating series, we end up with a set of equations of this type, which is labeled by a genus and a number of boundaries here. So you've got an infinite hierarchy of equations of this type. By the way, in the literature, if in this context you hear about loop equations, these equations, so Tutte's equations, these combinatorial properties, if you translate them in terms of generating functions, they are very often called loop equations. So that's a name that you will see in this setup.
Is there a tau?
Yeah, but I will not discuss it in this context. I will do that later today if I have some time. So what I didn't discuss up to now is what happened when you take omega G0, which doesn't depend on any variable. So the generating series of map of genus G without boundary. And out of that, you can build a tau function. I will discuss that, I hope, a bit later. Yeah, I'm not sure I will be able to do it this morning. Sorry? Yeah. Out of omega G1s, you can build of C. You can build some function which will become a big hierarchy of function. You've got to do some transformation. But yeah. What? It depends. So remember that I did some notation, which is that here I did forget about the T3 to TD and capital T. So actually here this depends on these parameters. I don't have any T1 and T2. So you remember that Tk is the weight that I associate to an unmarked face, which is a K-gon, and I don't allow unmarked 1 and 2 gons. So I just have all these numbers. If you want the T1 and T2, they are related to the capital T here.
All those quantities have the same dimension.
Sorry?
Dimension.
So these are just complex numbers. Yeah, but I don't want to talk about integral system. I will not have time for that. I'm sorry. OK, so yeah. What you've got to keep in mind, and maybe I should make this point now, is that I started from enumeration of maps. But when I'm saying that, what I say is that I want to count a weighted sum over the set of map of some given topology, so fixed genus and number of boundaries. Now, this weighted sum, it depends on the weights that I put on my unmarked faces, which are these TKs. So actually, when I say that I associate a surface sigma to such a problem, it's a family of them, which is parameterized by these numbers. So one way to think about it is that what I did do is consider a set of maps, so a set of what people could call discrete surfaces, and I did put a measure on it. And what I want to compute is an integral or a sum with respect to this measure. So I want to integrate over this discrete set with respect to a measure which depends on STs. And for each such measure, I can associate a Riemann surface sigma. And out of that, I will tell you how to compute all the omega GNs for arbitrary T's, just out of this data. So this knows about the measure. This has all the information about the measure I put on the set of maps. OK, so let's go back to the equation we have found, which is this one. I mean, this set of equations. And now I want to compute omega Gn plus 1 by induction. And the first thing I said is that, once again, you can use this equation in order to see that omega Gn plus 1 of Z1 of Z0 up to the n is, so before I was working with this function, here it's a meromorphic form in the variable Z0 to the n, meaning that we can think of it as a rational function in Z0 to the n multiplied by D0, D01, D2 up to Dn. And it has the following property. The first one is that if you C1 to the n, if you take one of your variable and you evaluate it at its inverse, it gets a minus sign. Except if, except in the case where G equals 0 and n equals 1, which means that this is true except if I consider omega 0, 2. And now, probably the most important part of the story and what will make that everything will work is that this equation, once again, allows me to know the singularity structure of this meromorphic form. 2G, for 2G minus 1 plus n, strictly positive. So meaning except for omega 0,1 and omega 0,2. Omega Gn plus 1 of Z0 to the n as poles in Z0 only at Z0 going to one of the branch points of my curve, plus or minus 1. Is there any question?
No one just answered the question.
Okay.
Are the P's
No.
do not know consistency of the equation?
Yeah, and what I will do is actually completely get rid of that. Yeah. So I don't know them. So I will project on a space where the P do not give any contribution. Yeah. Yeah. Indeed. And this follows from the definition. Okay. Maybe, is there any other question before I keep on going? No? So here I'm doing exactly as I did in the previous case for omega 0,1 and omega 0,2. I'm looking at this equation, and I want to extract the information I need. And the most important information for me is to say that I've got some well-defined meromorphic form in the z variables. And I want to know what kind of pole this meromorphic form have. And in order to do that, I just look at this equation, and I look at all possible poles which can occur. First problem which might arise is when x of z goes to infinity. Because in particular, so I will work by induction, so I will assume that for all topologies simpler than this one, meaning you remember that I said that if I make a recursion on the Euler characteristic, all the underlying objects have an Euler characteristic which is strictly bigger than the one coming from there. So by induction, I assume that all these objects satisfy this lemma. Now, if I look at this equation, still I've got a polynomial in x of z0. So it might have a singularity when x of z0 goes to infinity. But you see that I multiplied by omega 0,1 of z0 here. So if I want to compute omega gn plus 1, I've got to take the 1 over omega 0,1 there. And if you dx of z0 squared divided by omega 0,1 of z0. If you look at the behavior of this quantity when x of z0 goes to infinity, it is regular. And the reason for that is, again, that since pg n plus 1 of x of z0 z1 to n was defined by taking v prime of x of z0 times w gn of x of z0 x of z1 to x of zn, and taking the positive part and taking the product of the differentials here, 1 to n dx of zi. This bounds the degree of this polynomial by the degree of v prime minus 1. On the other end, omega, and actually degree of v prime minus 2, and actually this omega 0,1 behaves like v prime when x goes to infinity. So this is a completely irregular object. Okay. So now the way I did write it was that this is a function in, this is a polynomial in x0, but a differential in z1 to zn. And this is a polynomial in x0, but a differential in z1 to zn. Because, yeah, I don't need to look at this one. Okay. What? So, yeah, thank you. Okay, now, since I divide by omega 0,1 of c0, I can wonder what happened for the zeros of omega 0,1 of c0, which are not plus or minus 1. So, no, I didn't put it there. I want, yeah, sorry? So here I just, this definition is a polynomial in x of z0. Yeah, it's a degree n, so it's a differential form in z1 to zn. Okay, so Omega 0,1 of Z0 has some 0 when Z0 goes to plus or minus 1. But this one, I'm OK, because I want them. I'm saying that I want my omega gn plus 1 to have, to have a pole there. But it has some other zeros. And in order to prove that they don't give any contribution, meaning that omega gn plus 1 actually doesn't have any zeros, it's a similar argument to Brown's lemma. So I will not develop on that, but it's very similar to what we did for omega 0,2. Now, what else can happen? Here I've got some denominator, which are x of z0 minus x of zj. So I can have a pole when x of z0 goes to x of zj. This corresponds to two possibilities. First, z0 goes to zj. If you look at the equation that I mean, on a previous version of the equation I wrote before, actually, this denominator was coming from some wgn of x of z1. Oh, let's write it in omegas. Omega gn of z1 to z0 to n minus j minus omega gn of z1 to n divided by x of z0 minus x of zj, which exactly as in the case when g equals 0 and equals 1, is regular when z0 goes to zj, because the numerator and the denominator have a simple 0. So if you look in your notes, the first equation I got for this omega written in terms of w, the only place where this denominator appeared was in terms of this form. And so this is completely irregular when z0 goes to zj. So I don't have any pole. Now, if you look at it in this way, you could think that, no, if z0 goes to 1 over zj, you could have a pole, because this vanishes, but this doesn't vanish, a priori. Now, if you use the fact that you've got this skew symmetry property, if I've got a pole when z0 goes to 1 over zj, it means that I would have a pole when z0 goes to zj. So actually, I don't have a pole either. And z0 goes to 1 over zj by skew symmetry. Yeah. Yeah, so that's the coordinate I took. I will come back to this. So maybe I can remind you the shape of this surface sigma. One way to think about it is to say, I've got the complex plane here, which is parameterized by x. I've got 2 points here, which I call a plus and a minus. And if I take a generic point here on the surface sigma for a given value of x, I've got 2 points, which correspond to the 2 branches of solution to a quadratic equation. So above x, I've got 2 points, and I did find a global coordinate for sigma, because sigma is a double cover of the sphere ramified over 2 points. You can represent it in this way. It has genus 0. And you can find some global coordinate, let's call it z, where this corresponds to modulus of z smaller than 1, and modulus of z greater than 1. And above each point x, I generically have 2 points here, which I can call z of x and 1 over z of x. Where z of x is the one with the largest modulus. Now there's 2 points a plus and a minus. They are mapped to +1 and -1. And these are the only points such that the value of z and 1 over z coincide. Okay? These are called branch points because this is the place where, or ramification point, where there's 2 copies of the complex of the Riemann sphere just merged together. And they will play a very important role. Now, can I have any other singularity? If you look at it, you will see that by induction, it cannot have any other singularity because all these guys are already known. And by the induction hypothesis, I just have poles when z goes to plus and minus 1. So now, what does it mean? It means that I've got a very good knowledge of this differential as differential in Z0, for example. They are symmetric, so it's the same for all the other ones. But I've got a very good knowledge of this as differential in Z0, and I will use that in order to solve this equation. And this is exactly what we call topological recursion. So under this form, in a slightly different form, so this is the first time this topological recursion appeared, and it was derived in this setup by NR in 2004. And what does it tell you? It tells you that now if I want to compute omega g n plus 1 of Z0, Z1 to Zn, and I want to compute it except for the cases omega 0,1 and omega 0,2, so for 2g minus 1 plus n strictly positive. Then I've got a closed formula, which is the following one. I take a residue when a variable z goes to plus and minus 1, so it's a sum of 2 residues of this form. You take omega 0,2, where the first variable is 0, and the second variable is integrated from 1 over z to z. You divide it by 2 times, and you take omega 0,1, you evaluated at z, minus the same evaluated at 1 over z. And now comes the inductive part. So this part, so the residue, you see, it's a residue of at 2 very specific points, which are these 2 ramification points here. The first quantity I did write down here is composed only of the very special guy I studied first, the omega 0,1 and omega 0,2. And now what I have here is the following object. You take, in this equation, you just remove this part which you don't know, and this one which is kind of ugly, and you just keep this part, which is nice, and which you can know by induction. And you evaluate it at z1 over z, z1 to zn, plus, and now the other part is table sum. And here you've got 2 factors, omega g1 a plus 1 of z, a, omega g2 b plus 1 over z, b. Now if you look at the the Euler characteristic corresponding to this quantity, you can see that it is strictly smaller than the Euler characteristic corresponding to any of them. So this gives you an induction on this Euler characteristic. So it's an induction on 2g minus 2 plus n. So 2g minus 2 plus n corresponding to this side is strictly bigger than the one corresponding to any element here. And this is what is called topological recursion. Okay, great. So let me prove that. And yeah. This one? So I take omega 0, 2. It's a 2 form. So it's a 1 form in this 0, and it's a 1 form in another variable. And this variable, I integrate it from 1 over z to z. Yeah. Yeah. So should denote it in this way, maybe. Yeah. And so here it's just a difference. Okay. Keep that. Now, let's prove it. And nice, yeah. Sorry? Ah, yeah. Stable means that G1 A is different from, so you don't want to have G1 equals 0 and A empty, and you don't want to have G1 is equal to G, and A is equal to the full set. Okay? No, the second one tells you that, so yeah, I could write it in terms of B. I cannot have G2 equals 0 and B empty. Yeah. And the reason for that is that if I would allow that, I would have, for G1 equals 0, A being empty, I would have omega 0, 1, which is OK. But I would have omega G n plus 1, which is exactly the object I want to have. And one way to think about it is to say, if I would have taken the full sum here, I would have another term. But this other term, actually, I did compute it, and it gives me this part. So I could write this as another equation, which is 0 is equal to the same thing, where I remove the stable part. And yeah. It depends what you call right. Yeah. If no, one step to the right and below. So G and yeah. So in practice, what would I do? I start from omega 0, 1 and omega 0, 1 and omega 0, 2. And the first thing you can see is that for G equals 0, this doesn't give you anything. It's not there. So you can go on this way. Do you agree on that? Here I would have just a decomposition into subsets. Now once I've got all of them, I can get, for example, omega 1, 1. Just by the knowledge of, as you say, omega 0, 2 and actually omega 0, 1, which is there. In order to get this one, I need to know that, and so on.
Take your argument that the Euler characteristic goes down. For example, it would be like n goes down.
Yeah, so there.
In this case, before it went up, at one point you're at G plus 1.
Sorry? No, there is no G plus 1, never. No. So I'm saying that I'm doing an induction. Yeah. Yeah. So, yeah, the point is that, yeah, I wanted to make clear that why we call it topological recursion, because we've got, if we would like to see it as an induction on just one parameter, the Euler characteristic, the topology of your map is the important thing. But indeed, a better way to do it is to say it's an induction in some GN, which is ordered by some lexicographic order. And as you're saying, you can just first do this part and then increase. So. Yeah. 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 And yeah. Plus and minus. So I sum over two residues. So here I've got two residues. I've got a residue when z goes to +1 and a residue when z goes to -1. Yeah? No. No, I don't allow. I allow n equals 0, yeah. Here, yeah. So here, you mean this one? Yeah, I shouldn't have drawn it. It was a mistake. So the point is that the n equals 0 correspond to things which are not differential form on your curves. These are just function of the t and the small t and capital T. I will go back to that later on. There is a way to recover information about that. OK, is there any other question about the formula? So if you really want to make computation, and I will do it for the simplest cases, remember that I've got a very explicit expression of omega02 and omega01 in terms of z. And then here, I just have to make Taylor expansion of this object when z goes to plus and -1. And this will give me a formula for the omega GNs in this way, just computing simple residues. Now, where does it come from? And as you will see, it's surprisingly easy. Yeah? I will do that in the second part. I say, so the point is that I know that some people are not very comfortable with this kind of thing. This is a very nice example where you can work with rational function when you want to do computation, so you can see everything explicitly. So I think I will not have time to do that in the next lecture, but in the one after, I will talk about the formal neighborhoods, indeed. And that's a very important point, actually. Now, how do I prove that? So I want to compute omega g n plus 1 of z0, z1 to zn. So I could stare at this equation and say this is equal to 1 over 2 omega 01 times this. It's not far from this formula, but I've got a bunch of terms which are not there. And in particular, there is one I don't know in this equation. In order to get rid of that, just use Cauchy formula. I write it as residue when z goes to z0 of omega gn plus 1 of z, z1 to n. And in order to compute it, so here, remember that this is a differential form in z1 to zn, which is the same as here. This is a differential form in z, so I can integrate it in order to compute the residue. And this is a differential form in z0, which I don't have here. So I write it as dz0 divided by z minus c0. This is just Cauchy formula. No, I didn't do all the work before for nothing. The good thing I know is that this object here has poles only when z goes to plus and minus 1. So I can move my integration contour. Mainly, I'm saying that here I've got rational function in z. So the sum of the residues should be vanishing. And here, the only pole of this product are when z goes to z0 and z goes to plus and minus 1. So it's equal to minus residue when z goes to plus and minus 1. So it's a sum of two residues of the same quantity. Now, in order to later get a formula which is a bit nicer, sorry? No, this has a dz. Yeah, but this has a dz. Yeah, but this has a dz, but it doesn't have any dz0. But this has a dz0, so I've got to have it here. So yeah, I really mean it. I could put it, I could put it outside the residue if you wish. So I've got omega g n plus 1 of z0, z1 to 1. Now, you remember that if I change z into 1 over z, I get the same quantity, but with a minus sign. So I could do that, and then make a change of variable. Z goes to 1 over z. I will get exactly the same expression, but with a plus sign here. And the price to pay is just to change z to 1 over z here. And so I've got two terms which give the same result, so I can take the average. And it gives me the following equation. 1/2 residue when z goes to plus 1 and minus 1 of, and here I've got two terms, dz0 divided, so the first one is this one. I put the minus sign inside. It takes the form z0 minus z, minus the one where I change z to 1 over z. Multiplied by omega g n of z, z1 to 1. Now, the first thing you can observe is that, yeah, plus 1. Thank you. The first observation is that actually this can be written in terms of omega 0,2, which you remember was a very nice object, which was just dz0, dz1 divided by 0 minus z1 squared. So if you integrate it, you get something with simple poles. And so if you integrate it, you've got simple pole when z0 goes to z, z0 goes to 1 over z, which is exactly this quantity here. So I could write it in this form. Z of omega 0,2 of z0 times omega g n plus 1 of z. So you see that the dz0, which I had here, was taken into account in the omega 0,2, which is a one form in z0. And when you integrate it, it is a one form in z0, but it's a function of z. Yeah. So I'm just looking at this, and I change z to 1 over z. So I'm making a change of variable here. What? Yeah, sorry. Yeah, yes, that's the question. Yeah, so it's a sum of two residues. You've got two residues. So yeah, maybe I should write it here. Residue z goes to plus and minus 1 is equal to residue when z goes to plus 1 plus residue when z goes to minus 1. Yeah, that's a notation. I'm sorry. No, I'm almost there, actually. So you see that I've got this integral here, which is this part. But I still have the object I want to compute. I don't have the result. But now I've got this equation. I take the 1 over 2 omega 0, 1 of z0 downstairs. It gives me 1 over 2 residue. Z goes to plus 1 or minus 1. Integral from 1 over z to z of omega 0,2 of z0 divided by 2 times omega 0, 1 of z. And let's say that all this part, I call it right-hand side of C0 to Cn. So here I will have right-hand side of C1 to Cn. So I'm just taking the 1 over 2 omega C0, put it downstairs on the other side, and I get this equation. So before completely finishing the proof, no, you remember that omega 0, 1 has this property of being skew-symmetric when you exchange C and 1 over C. So actually, even if this looks a complicated way to write it down, omega 0, 1 of Z minus omega 0, 1 of 1 over Z is equal to 2 times omega 0, 1 of Z. So I would write it as omega 0, 2 of Z0 dot. And here I replace it by omega 0, 1 of Z minus omega 0, 1 of 1 over Z times the right-hand side of my loop equation. Okay? Now I'm really close to ending the proof. You see that in the right-hand side, I've got one part which gives me exactly the contribution I want here. So this I will keep. I will not think about it anymore. But what about the leftover? The first thing and the most important point is that this was the only object I didn't know by the induction hypothesis. But that's a nice guy. This is a polynomial in x of Z0. And so if you look at P, G, n plus 1 of x of Z0, C1 to n, dx of Z0 squared, and you divide by omega 0, 1. Yeah. So I look at this quantity. Yeah. Now I'm looking at this, and I want to have this factor times this polynomial, and I want to compute its residue when z goes to plus or minus 1. First, let's look at this object. Does it have any pole when z goes to plus and minus 1? The numerator has a simple 0, because this is vanishing when z goes to plus and minus 1, because that's the case where z and 1 over z coincide. This has actually a double 0, because, yeah. So this has a double 0 because, sorry? Which one? Yeah. So if I look at it as a, so this is a function of z. Yeah. So this is a differential. My no, it doesn't have any poles at the point. So it has only, yeah, that's the only one which doesn't have pole at the branch point, at plus and minus 1. Yeah. So just to remind you, omega 0, 2 of Z0, Z1 has only one pole, and it's when Z1 goes to Z0. So it doesn't see the branch points plus and minus 1. Doesn't have any particular behaviors there. So this has a simple 0, and this has a double 0. Because this you remember, you can write it as y of z dx of z, which I can write, if you want, x prime of z dz. X prime of z is vanishing when z goes to plus and minus 1. And basically, that's the definition of this point. And y of z turns out to have, you remember you had the square root, so you've got a simple 0 as well when z goes to plus and minus 1, so this has a double 0. So this big object has a simple pole when z goes to plus 1 or minus 1. Okay. Now, I multiply something which has a simple pole by this polynomial in x of z times dx of z squared. This is completely irregular. It's a polynomial. It doesn't have any pole at the branch point. But dx of z is x prime of z times dz as a 0. So if you take the square, it has a double 0. So actually, this times that is a double 0 times a simple pole. So it is actually vanishing, and in particular, it doesn't give any contribution to the residue. It doesn't have any pole when z goes to plus and minus 1. So it means that when I compute that in the right-hand side term, I can forget about it. Now, if I look at this object, it's something which is very similar. It's dx of z0 squared, which has a double 0, times a rational function in x of z0, which doesn't have any pole at the branch point. So you can use exactly the same argument. Doesn't give any contribution. So I'm just left with one object here, one term in my sum, a sum of n terms. And the question is whether this gives any contribution. So I'm left with the term of this form, dx of z dx of zj divided by x of z minus x of zj squared omega gn of z0 to of z c1 to n, where I removed cj. So a priori, I don't have any simple argument as the one I had here, because this might have poles when z goes to plus and minus 1 by the induction hypothesis. But this term has a very peculiar behavior compared to the other ones. If you look at it, this is symmetric under z goes to 1, z0 goes to 1 over 0. This one as well, this one as well. But this one is Q-symmetric when z goes to 1 over z, or z0 goes to 1 over z0. So this is Q-symmetric when z goes to 1 over z. But no, how does the factor here behave? When z goes to 1 over z, this changes sign, this changes sign, so this is symmetric. So I'm computing residue of something which is symmetric times Q-symmetric, so I've got a residue of something which is Q-symmetric under z goes to 1 over z. And now if I would make the change of variable z goes to 1 over z for my integration, I would get exactly the same result with 1 over z, but because of the skew symmetry, there's two terms cancel. So actually, when I'm writing down this, here the only important part here is the part which is symmetric under z to 1 over z. Everything which will be skew symmetric doesn't give any contribution. And so this gives 0 by skew symmetry. So I'm just using the symmetry of this residue when z goes to 1 over z. So it's a slightly different argument compared to the other one, but the output is the same. Yeah. 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 So here, yeah, I've got minus, minus, so this is symmetric. But no, this term, the factor which I'm considering now, is Q-symmetric. And that's the reason why it doesn't give any contribution. So the fact that indeed here I've got something which is symmetric makes that here the only contribution will come from symmetric function, or symmetric differentials. OK? And so I don't have this part, or this part. I just have this. And that's exactly the recursion, the topological recursion, which is this formula, which I did write down. So one way to think about it is the following one. I started from this omega g n plus 1, which is a differential in Z0, which actually I can write down using this equation. The point is that there are things which I don't know by induction. In order to get rid of them, what I do is that I use the fact that I already know that this is a differential which has poles only at plus and minus 1. And by using this Cauchy formula and moving the integration contour, I'm projecting this function on this differential on the space of differential, which have pole only at plus and minus 1. So you can think of this procedure of taking residue here times this part as projection to the space of differential, which have pole only when z goes to plus and minus 1. When I project there, all these ingredients do not give me any contribution. And that's the idea behind the recursion. You've got an expression which is very complicated, or too complicated, and there are some not meaningful information which you kill by projecting on the right space of differentials. OK, so I think it's a good time for having a break. And after the break, I will give you an example of computation and try to represent that graphically to see what's going on. So first, as Francois has pointed out, I didn't finish the proof because I've got z and z. And it just showed me that I forgot, I did something wrong here, which is that there should be a minus sign here. If you make the computation, here you will have the same with a minus sign. So it's just a overall minus sign all over here. And so now I'm here, and I've got the right-hand side, where I've got this expression with z, 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 and z. It's not quite what I've got there, because in what I've got there, I've got z and 1 over z. But you remember that I've got the skew symmetry property, so I can exchange one of the variable to its inverse, and the price to pay is to change the sign. And that's the reason why you go from this minus sign to a plus sign. So here I should write it as right-hand side of z, cz1 to the n. And then I can flip one of them to get z 1 over z. OK. Yeah, is there any other question about this? OK, so I can erase that. And tell you one way of thinking of this equation. So there are different representations of this equation, and I will first give you maybe the most convenient one when you want to do computation, which is the following one. Let's represent omega gn plus 1 of z0, z1 to n, in the following form. Remember, it's a generating series for maps of genus G, so I represent it as a genus G surface, so a surface with G holes inside, with n plus 1 boundaries, which are associated to variable z0 to zn respectively. And I did make the choice to treat z0 a bit differently, so I put it there. And I draw it then as genus G surface with n mark point, or let's put it in this way, n outgoing edges, which correspond to the n plus 1 boundary of my surface. What does the recursion tell me? And in particular, what is this big factor on the right side? So I want to compute this. Z0, Z1 to the n. I want to have a kind of induction on the topology of my surface. I wanted to make it simpler by some procedure. What kind of procedure can I follow? What I can follow is, say, I can pinch a cycle there in order to simplify my topology. And so what I will do is start from this point here, and I look at a cycle on my blob surface, which come back here, so which is based there. So for example, this one. Now, I wonder what happens if I pinch it. I get a surface of this type, so this gets pinched, gives me this big hole. I've got my original Z0 here, and I've got C1 to the answer. So Z0 really sits, so what I'm doing is just pinching there, so it really sits there. And now I will go a bit further. What I will say is that I will replace that by just a trivalent vertex. Z0, and so I just making it very thin. And I represent it in this way, and then I keep my surface here. With C1 to the n, and I've got 2 holes here. Now if I do that, and here on the right-hand side, I've got a picture which is of the same type as before, it would be something which contributes to omega g minus 1, because I replaced one of the holes by this kind of loop here. And in terms of variable, I've got the original z1 to the n, but I've got 2 of them in addition, and I will label them by some z and 1 over z. And you see that if you look at this part, this I can think of it as omega g minus 1 n plus 2 of z 1 over z, z1 to the n, which is the first factor here. So here I just gave you an intuition of how I could get such factor. I can think of it as a degeneration of my original surface. Now I look at a very, yeah? Because that's what I will have in the equation, yeah. So a priori it should be, it could be z and z prime. But I just want to have a representation of the equation I've got here. So now the first thing I want to do is to make sense of these factors there and this big sum, yeah? So it can be related to that, and I will talk about it in another representation. I should say that in general, for the moment, this doesn't have a very good geometrical interpretation in general. And in particular, in this map setup, this is a representation. I cannot give you a good geometrical intuition of that. Just giving you an intuition of the different term you get there. Now here I did choose a cycle such that when I pinch it, so if I would take this one or this one, it would be the same. I do not disconnect the surface. But I could have taken something of this type. C1 to the n, C0. And pinching it along such a cycle, where here I've got all the elements CA, and here all the elements CB. And if I pinch it, what I get, and I do exactly the same procedure, the point is that I disconnect it into 2 parts. One of genus G1, another one of genus G2. And I get something of this type, Z0, Z prime, if you want, ZA, ZB, genus G1 on one side and genus G2 on the other side. So you can really think of this quite big sum a priori as coming from degeneration of surfaces of this type. And what I did is that I did replace this pinch cycle by a trivalent vertex. Okay. Yeah, is there something you cannot read? I called it Z prime, as you wanted. Now the representation I will have of this recursion is coming from there. And what I will do is represent it in the following way. You take your omega g n plus 1, C2, and I will say that it's equal to something of this type. So you've got your trivalent vertex, which comes from this pinch cycle. So 0 is some kind of origin, some root. So it plays a very particular role. I associate to a vertex a point Z, which is a dummy variable. Cn, I should write it in this way. So these are the two degeneration I. Sorry? Yeah. Plus, and you make the sum over stable ones of the same thing. So you've got your trivalent vertex going from Z0 to Z. And here you make your CA, CB. And I will take the residue when Z goes to plus and minus 1. So once again, this is a sum of two residues. And what I mean there is that this will represent omega g n plus 1 of Z0 Cn. Now what about the trivalent vertex? It's the integral from 1 over Z to Z of omega 0, 2 of Z0 divided by omega 0, 1, 2 times omega 0, 1 of Z minus omega 0, 1 of 1 over Z. Up. And actually, you see that for the following here, you need to know which leg is associated to Z or 1 over Z. And I will do that by just adding a marking. So I've got an orientation on my trivalent vertices saying that on this side I will have the variable Z, and on this side the variable 1 over Z. So this means that this corresponds to Z, and this corresponds to 1 over Z. So this is just a representation of this expression. The first good thing is that by this procedure, you see that the topology simplifies in this equation. So you really see that it's an induction. No, the second thing is that yeah, should keep that, sorry. That's what comes from the equation. Where? Here? This one? This one? So in the proof, actually, what I got was the same integral with Z downstairs and 1 over Z upstairs, and Z and Z. Yeah. Yeah. Now, the point is that this is Q-symmetric when I exchange Z and 1 over Z in one of the variable. So one of the Zi, if I take it to 1 over Zi, I get a minus sign. So I can do that here. Just so how could I state that? If you just look at this equation, so for example, the way Bertrand and I found the expression was quite different at the beginning. No, what we like in general is that this involution z goes to 1 over z will play a very important role in the following. And this is nicer to have something which behaves like which has this form for some general properties. Yeah, I will come to that, I hope, in a few minutes. So there will be local involution. I will tell you about this after. So as you see, there are different things here which are kind of cosmetic, and you wonder why I did that. So there is this 1 over z here. I told you as well that I write it in this way, but I could just remove that, and I have a 2 here. I could do something similar actually here, just having just integral to z. No. You say on skew symmetric in Z0 with respect to what? No, but you want to have +1 and -1. Yeah. Okay. Yeah. Yeah. I could do that. Yeah. But this is once again, this is a very particular case of the general topological recursion, and I want you to be ready to have the general formula. So yeah, in this case, I could do that. Yeah, this will come. So maybe we forget about all this question about the general setup because I didn't introduce it yet, and we'll do that later. Okay? But I will reply to your question. Yeah, you will see it. Okay, so I've got this equation. I just represent it in this way. So first, it shows you that it's really an induction. And the second thing is that, no, once you did it one step, you can keep on doing that. And what you end up is that you've got a representation of your omega g n plus 1 as what? So you keep on doing that. What you end up is, OK, I do that here. I will have some trivial vertex. For example, I can cut this into 2 disconnected components. I keep on going. And when do I stop? I stop when I cannot decompose it anymore, which means that I end up with something like that, where one of the components is just a genus 0 surface with 1 ingoing and 1 outgoing leg, meaning that this corresponds to omega 0,2. And you can follow this step, and what you will find out is that you can write this just as a sum over trees, which has a very particular shape, which will be of this type. You've got a spanning skeleton tree, which is a rod corresponding to these vertices. And let's do that here. And you've got a bunch of unmarked edges. So if you follow this step and you replace omega 0,2, which with my notation should be something like that, Z1, Z2. You replace it just by an edge going from Z1 to Z2, non-oriented because it's symmetric. Then you will find out that this can be written as a sum over trees of this type. Sorry? It might have loops. There is one loop, so it would correspond. So that's what I'm saying. There is a tree of arrowed edges, no loops. No, you might have loops, and these loops will be created by non-arrowed edges, so non-oriented edges. But there will be some selection rule which states that I cannot have a loop going from one branch to another branch, saying that I can just link together by some non-oriented edge two vertices which are in the same, one being the descendant of the other one with respect to the partial ordering given by your arrowed edges. So then you want to associate a weight to that in order to get your omega gn. What you do is that this you associate some omega 0,2. So you associate to each vertex Z1, Z2, Z3, Z4, Z5, Z6, some Doomy variable. Then this corresponds to something, some variable Z0, Z1, Z2. So the leaves are labeled by your variable here, C5. And so the weight associated to such a graph is simply taken in this way. Whenever you've got an edges linking two vertices of type Zi to Zj, you replace it by some omega 02. Yeah. The only rule is that you cannot, for example, link this one with this one, but you could link this one with this one, for example. Yeah. So, yeah, you could have something like that, for example. C1, C2, C3. This would contribute to omega 0, 3. And you've got to integrate over 3 variables. You've got 3 vertices. Yeah. So now let me finish. So my representation is that when it's non-oriented edge, I've got some omega 02. When it's an oriented edge, I use this. If I call this K of Z0, Z, I replace it by K of Z2, C3, which is not symmetric with respect to the exchange of Z2 and Z3. I make the product of all these quantities, and I just take a residue when all these internal vertices go to plus and minus 1, and I make the sum. So this is a representation of the recursion, and it's very convenient for doing computations. Yeah? Yeah, I will do it just right now. No. Because you've got these non-local rules which states that you cannot have loops going from 0 to 0, for example. No, so definitely not. Okay, so yeah, maybe. So just regarding your question originally between the relation between Z and 1 over Z, whether it was related to length and so on, another way to think of that is to say, instead of thinking of pinching a cycle, could look at this surface as being a surface with boundaries, n+1 boundaries. And now I look at, with a first boundary, say 0, and I look at pairs of pans embedded in this surface with one of the boundary components being the one I choose to start with. For example, this one. And indeed, in some example where you can apply that to hyperbolic geometry, the rules to have this Z and 1 over Z tells you that you integrate over some moduli space of pairs of pans whose boundary are geodesics of respective lengths L0, L1, and L2. And this is related to that. So maybe I will talk about that later in the lectures. This is related to the work of Mirsarani on the volume of moduli space of Riemann surfaces. So another way to think of this degeneration is to say, I've got a Riemann surface or surface with boundary, n+1 boundary component, and it has genus T, and I just look at all possible ways to embed a pair of pants in my surface, such that one of the boundary components of this pair of pants is the boundary I consider, and I look at what happened when I remove it. And this gives me exactly all the terms here. And this is probably the best explanation for the geometry behind this equation. Now, this representation is a very convenient tool. If you want to see the detail of the set of graphs that you get here, once again, you can look at the book counting surfaces by Bertrand and Henard. The set of graphs you get is described explicitly, and there are many examples here. But this is a set of graphs because of this kind of selection rule for the loops, which makes that they are really not arbitrary at all. And for example, the number of such graphs doesn't grow very fast when n and g grow. And that's a very Good thing if you want to do computation, it means that if you want to implement that, for example, on a computer, the number of terms that you will have to consider in order to make your residue computation doesn't grow too fast. So let's look at some example. C plus 1, omega 0, 3 of Z1, C2, C3. So first, I would like you to see this graphical interpretation. Z0, Z1, Z1, Z2, Z3. Okay, let's take Z0, Z1, Z2 if you want. Z0, Z1, Z2. Yep. No, it is not. G times, how do you see that? Yeah, you've got a subset of n, yeah. Yeah. Yeah, but in G it doesn't grow that, yeah, okay, yeah. Yeah, no, I mean this restriction I was talking about has to do with the genus. Because there are many cases where you're interested in what happens, for example, for a genus, and this is a nice thing which is there. But yeah, no, in N you don't. So if you look, for example, at what? Sorry? Yeah. Yeah. Yeah, you will have to consider. Yeah. Yeah, but it's not n to the power n, which is no, it's not polynomial. Yeah. So what was the contribution I would get? So I look at all possible ways of pinching this. And it's very easy. You just have two possibilities. So in the first representation, I would have this, where this is omega 0, 2. But you remember, I just replace it by just one edge, Z1, Z2, with some Z here. And now I've got to say on which side I put my Z and which side I put my 1 over Z. So actually, I've got two contributions. C2. And now maybe, Francois, I can go back to your question, which was why do I have Z and 1 over Z here? Another useful property of this definition is that I don't have any symmetry factor here. I don't have to say that I've got the same graph 2 times. I've got 2 different graphs because I desymmetrize the vertex. Okay, so that's the representation. It's pretty simple. And now if I write it down explicitly, I've got residue when Z goes to 1, integral from 1 over Z to Z omega 0, 2 of Z0. With a 2 here. And here I just have 2 terms, omega 0, 2 of Z1, which is the first one, omega 0, 2 corresponding to this edge, omega 0, 2 of 1 over Z2. Plus the contribution coming from there, omega 0, 2 of Z2, omega 0, 2 of 1 over Z1, plus the residue when Z goes to -1 of the same thing. No, yeah, I'm going to remove that. Now you've got some explicit expression of omega 0, 2 in terms of Z. Just dz1, dz2 divided by z1 minus z2 squared. And omega 0, 1 you write it as y of z dx of z, where you've got an expression of y and x as rational function of z, coming from the previous lecture. So I gave you a recipe to get this, the explicit expression for these rational functions. And if you just make the computation here, you will end up with this formula. C0, C1, C2, which is the sum of two terms. So you've got a 1 minus 1 over, sorry? Which one? This one, yeah, so let's give me the same, yeah. So that's why I said that here I did, in the equations there, I did make a choice to have one side corresponding to z and the other one corresponding to 1 over z, just to make sure that actually here I know that there are two contributions, so there should be a symmetry factor of 2 associated to this graph. But the good thing with this representation is that there is no symmetry factor. So I write it in as 2 terms, but it's only 1 times 2. So I write it in, you get it in this way. It's y prime of 1. So you remember gamma is a quantity you can compute, and y prime is the derivative of y evaluated at z equals 1. And then you've got a product from I equals 0 to 2 of dzi divided by zi minus 1 square plus 1 over 2 gamma y prime of minus 1 product from I equals 0 to 2 dzi divided by zi plus 1 squared. So here you can read all the property we know of omega 0,3. The first one, which is not obvious from the recursion formula, it is indeed symmetric in Z0, Z1, Z2. We're happy about that, because if you look at this formula, this is not at all symmetric under the exchange of Z0 with any of the other Zi's. But the result is. We can see that it has poles only when one of the Zi goes to plus or minus 1. And we know the degree. In this case, it's just equal to 2. Now, let's look at an example with one loop. So gamma, we computed it last week. It was a representation of your A plus or minus, which was equal to, what was it, alpha plus or minus 2 gamma, I think. Was it? I guess that's what I did take as notation. So there is this recipe to obtain gamma as a function of the TKs, which are the way to associate with the unmarked faces. So you can think of this gamma and this y function as function of the weight TK you put there. Yeah.
In terms of that, you're the polynomial n.
So yeah, so y of z is equal to m of x of z square root of x of z minus a plus x of z minus a minus. And it has a nice expression in terms of the z variable. Sorry? Of m? It's degree of v prime minus 1. So that's. Yeah, but we did it last week. We did it. All the information about this polynomial is encoded there. So we do it once for all. Yeah. But we have to do it. Because if I don't know this curve, I cannot do anything. Because I don't know the change of variable x to z, for example. But yeah, we need to do it, but we do it once for all. And if you want, you've got one you've got a family of y's which are parameterized by the tk's, which are the parameter of my enumerative problem. Everything can be computed. So if you start from, yeah, yeah, and I even gave you a recipe to compute them as function of this. So if you follow the lectures, you've got a way, for example, for quadrangulation, I gave you a way, I gave you how to compute y and x in terms of this. So you know them, and now you just have to plug them in this expression. Okay. So yeah, if you want, there are 2 steps in this procedure. I will come back to that, but the first step is find this curve, and finding this curve comes from the knowledge of this W01, some combinatorial equation which are imposed by that. But once you've got this, it means that you know your y, you know your x, and you know your gamma. Then you just apply this recursion, and you know all the terms. Yeah. They just come from the. Sorry?
Does it make any sense to have no t?
No t's. So t's are just parameters which I can fix to specific values. So you want to have all the t's vanishing?
Yeah.
That's your question?
Is there an explicit way to write n for t?
Yeah. So it will correspond to a model where so your maps will be empty. You don't have faces, so it's an enumeration of graphs. So what corresponding to the length of the boundary here will correspond to, so it will be an enumeration of trees actually, of graphs. And the length of the boundary will be related to the number of, to the degree of the face around your graph. I'm sorry, I didn't follow you lecture. But yeah, I should mention, you know it perfectly. It's the Gaussian and one matrix model. So yeah, you know it. Okay, let's go there. I use this representation now. Got my Z0. And I say it's equal to what? Here I don't have much choice. I don't have any way to disconnect my surface. There is only one cycle, so it's a trivalent vertex. And a priori, I would have a genus 0 surface with 2 edges. So I would pinch it here. So what I get is something like that, which I represent as trivalent vertex with something of this type. So genus 0 surface with 2 mark points or 2 boundaries. So it's some omega 02, which I represent just by one non-oriented edge. Okay? And then you will see the second. Yeah. And they are the same. Yeah. So that's a particular case. So you can have loops based on the same point. Sorry? Yeah. And then the marking, you just have one contribution in this case. No, because there is another selection rule for the marking, which is that when you've got loops, you have just basically one way to choose the marking for the ancestor. You will always put it on one side. So that's why I say if you want the specific rule for the set of graph, you should look at this. I don't want to discuss that because there is a list of 11 rules, I would say, and it's pretty long. And if you just want to do computations, you can just follow this procedure. But if you want to study the set of graph, the rules are non-local and not that easy to state. Okay, so I've got this, and now you will see the reason why we've got this 1 over z. So I take exactly the same. So I will call it, as I did before, k of z0 z. And now this is the weight of this part, z0 going to z. And now what do I get? I've got some omega 02 of z 1 over z. Now you see that if I wouldn't have made this z goes to 1 over z, actually, I could have an issue here, which is that this has a pole on the diagonal, so this would not be that well defined. No, you can compute it explicitly, and if you want to see the result, it's just take this form, 16 gamma y prime of minus 1, 1 over C0 to the power 4, minus 1 over C0 plus 1 to the power 3, minus 1 minus y second of minus 1 divided by y prime of minus 1 plus y third derivative of minus 1 divided by 3 y prime of minus 1. And this is the order C0 plus 1 squared. So this is for the contribution of minus 1. And you've got a very similar contribution for plus 1, which is 1 over 16 gamma y prime of 1, 1 over C0 minus 1 to the power 4. Sorry? If you want, OK. Minus C0 goes to 1 over C0. Yeah, and that's it. Plus. Yeah, no, the point is that also, yeah, but if you exchange C0 to 1 over C0, you will get, yeah. Sorry? No, yeah. No, what? No, yeah. No, it's minus 1, yeah. So, no, you don't change anything. So you just keep that, yeah, it's not true. So you've got a similar term, 16 gamma, yeah, no, it's completely different. Sorry. I mean, you just take the same thing, you change 1 to minus 1, but there are some signs which are changed. C0 minus 1 to the power 4. I think it's a plus here. Plus 1 over C0 minus 1 to the power 3. Minus, and here it's 1. Plus in the same term. Plus 1, 3 times y prime of 1. And this gives you the order 2 pole at 1. So I just did write down the result of this computation. Once again, it's completely explicit in terms of y and the z's. And we can see the structure. It still has poles when z0 goes to plus or minus, to minus or plus 1. But you see that the order of the pole is bigger than the one we had here. And actually, what you can check by recursion is that indeed the order of possible poles increases with g and n, and it increases to as 6g minus 6 plus 2n, I think. But we'll come back to that later. So is it OK for the loop case? Is it a bit more clear, or do you want another example of graph? OK, so it's going to be all for the enumeration of maps. But now I just want to remind you of all this procedure just to motivate what I will do next week in this general topological recursion. So the starting point, the question is the enumeration of maps. One way to think about that is to say, I've got some set mg L1 to Ln. So a set of maps of given genus with n boundary components of respective lengths L1 to Ln. And I put a measure on this set. So measure d mu, which depends on some parameter T3 to Td capital T. So that's exactly what I did. I did write some weighted sum over element of this set, and I gave a weight to each of these elements. And this weight was depended on some parameter, T3 to TD. So that's like putting a discrete measure there. And what did I want to compute? This TG L1 to Ln. You can think of it as integrals, in this case these are sum, over this space of map, this set of maps, which can be thought as a space of surfaces with a discrete measure. Integral over that of the measure d mu. So really the problem I have, some people would interpret it as computed integral over a moduli space of genus G surface with n boundary component. And this integral, I do it with respect to a very specific measure. You could think of it as a measure which localizes only on some discrete surfaces, some triangulations. Yeah. To M, to N.
You have L for N and T for T.
So it has nothing to do. So T sub D. Yeah. So it has nothing to do. D is the maximal degree of the unmarked face I can have in my maps. And so L can range from 1 to infinity. Yeah, of T's, yeah, exactly. Yeah. So that's one way of thinking about that. Starting from there, I just looked at the simplest element, T0L, and I did build a generating series in this way. So just an asymptotic when x is large. A priori, it doesn't have nice property, but it turns out that its solution to an algebraic equation and this defines for me some Riemann surface sigma, which is called the spectral curve. So I start from this set. I've got a kind of measure on this space of maps. I want to compute integral. I look at the simplest space, which is the one corresponding to G equals 0 and just one boundary component. I built a nice generating series, and I can associate to this problem for an arbitrary measure a surface, and actually a family of surfaces which are parameterized by this T3 to TD and T. So the type of measure. To each measure, I can associate a surface. Now I did compute my W02, which is a very nice object on this surface. And then I did just compute this WGN. I promote them to differential form. I can show that they are well-defined meromorphic form on the same surface. And I've got a nice formula here. And now what is this formula? And it will be the motivation for the following. What do I need for that? I need not many things. I need this surface built as a cover of, in this case, P1. And I need to know the ramification points of this cover. So in this case, just plus and minus 1. So I will compute always omega Gn as residue at branch point of some cover of P1. In this case, this specific cover. Of some integral, which I will have to define later, of omega 02 divided by something which depends on omega 01. And this can be defined it is just a formula which depends on GNA. Now the question is, what happens if I would replace sigma by some other Riemann surface, which doesn't come from this case? Do I get something interesting? So that's the construction I will do next time. This is the topological recursion setup. And it turns out that for many problems of enumerative geometry, for example, for the computation of Gromov-Fulton invariants, which can be thought as some integral over some moduli space of Riemann surfaces, not discrete Riemann surfaces with respect to some measure, you can do the same thing. You can build some W01 of x, which defines for your Riemann surface. And if you apply the topological recursion, what you get is that if this was some integral over the moduli space of genus 0 surfaces with one boundary, the WGN will be integral over the moduli space of genus G surfaces with n boundary components. And this is very powerful in the sense that this formula will always be the same. The only thing you will change is this surface. And I would say the goal of the understanding of this topological recursion would be to have a very nice interpretation of this interplay between choice of measure on this space of surfaces you want to enumerate and this surface. And for those who know about this, this is closely related to mirror symmetry. So I will discuss that in 2 weeks from now, the general formalism, and give you some example of application which go more in the geometrical side. Yeah, I will stop here. Sorry? So the point I think Don was making earlier is that here we're just computing a residue at these ramification points. So actually the only information we need to know is the Taylor expansion of omega 02 and omega 01 at this branch point. So actually we just need to know some series, some expansion of this guy. So we don't need any algebraic curve. We just need some formal disk around these points. And yeah, and this is a very powerful setup. So you can forget even the kind of global structure of your curve here. The point being that if you want to have nice property of the object you built, so you always have nice properties, but if this is an algebraic curve, you've got even nicer property. And for example, integrability is believed to be related to such behavior. Okay.